I'm back, everybody. Hope we're all having a good day today. Again, this is like minutes after I finished the first video, but it's a couple days after for you guys. So, I mean, I'm still wearing the same clothes. I got my Golden Grove t-shirt on. But I hope everybody's staying healthy, and I hope we're all keeping busy. I'm gonna wear a hat from here on out because my hair is getting really weird. Like it's getting long on the side. Yeah, whatever. And I like live in hats when I'm not at school. So, okay. So we did section A4 day 1, and it was due on Tuesday. And now this section A4 day 2 is due on Thursday. The assignment is, at least. You're probably watching it on Wednesday. No assignment, obviously, on Friday. So after this video, after this assignment, nothing till the next week. No quiz on Friday or anything like that. All right, so let's jump in. Let's get to it. So on the first lesson, we learned about what is a hyperbola, the graph of r 1 over x, and how to transform it, how to move it left, right, up, down, and also multiplying on the top means a vertical stretch or compression. And we learned what that means in terms of the asymptotes, whether I move them left, right, up, down, whatever. Okay. Now, in this section, and then we talked about the rules about how to find the vertical asymptotes and the rules how to find the zeros of the function. But we have not talked about, and like in terms of that last example, what does that imply about the horizontal asymptote? We talked about vertical asymptotes, but we did not talk about horizontal asymptotes when it's not in that that strict. We had that. What was it? A over x minus h plus k. When it's not in that form, when I put a polynomial instead of just a single number up top, that's when it shifts a little bit, and we have to do our new rules about. Okay, this is when you set the numerator equal to 0, set the denominator equal to 0, find your zeros, find the asymptote, right? When it's not in that form, when it's not in this form, how do you find where the horizontal asymptote is? Okay. So let's get going here. Some rational functions, including those whose graphs are hyperbolas, have a horizontal asymptote. So the existence and the location depend on the degrees of the polynomial that make up the rational function. So we're looking at the degrees of each polynomial. So we've got p of x on top, and I'll scroll down here so you can see all of it. Stuck on my face. Why not? I'll leave it at whatever. You might want to jot things down. That might be a good idea. I'll move myself into more of the corner. There we go. This would be a good thing to write down. So you might want to pause right here. Okay, we'll play. So it's saying that let f of x be p of x over q of x, right? Where p of x and q of x are just two rational expressions in the numerator and denominator. Oh, got to turn around. That's fine. Okay, so p of x and q of x, those are just the polynomials in the numerator and denominator. Okay, so, and it's important to note, and I didn't even say it on the last one because it doesn't really affect anything. They can't have any common factors. We're going to figure out what happens when they have common factors, but they can't have any common factors. Okay, so we're going to have to factor them down and then factor out things that they have in common, but not just quite yet. Now, the graph. What are the rules about the horizontal asymptotes? Okay, if it's top heavy, that's when I say top heavy, that means the degree in p, the degree in the numerator is bigger than the degree in the denominator. Okay? The degree in the numerator is bigger than the degree in the denominator. It's got a higher degree on top than it does on bottom. There is no horizontal asymptote. Okay? There is no horizontal asymptote. That, coincidentally, was what we studied, like those couple problems that we did at the end of the last lesson. If you look back, the degree in the numerator is higher than the degree in the denominator. So there wasn't even a chance of having a horizontal asymptote. That's why we did those then. Now, if it's flipped around, if it's bottom heavy, if the degree in the numerator is less, if the degree in the denominator is bigger than the degree in the numerator, okay? If it's bottom heavy, if the degree on the top is less than the degree on the one on the bottom, the horizontal asymptote is at 0, okay? At y equals 0, which makes sense because, if I just have 1 over x, right, just our parent, where is the horizontal asymptote? Well, it's at y equals 0, right? It's right on that horizontal line, right? Right on the axis there, right? okay, at y equals 0. If, last option here, if it's equal, right? So we had if the numerator was bigger, if the denominator was bigger, if it's equal, then what you look at is the leading coefficients, the leading coefficient of the top versus the leading coefficient of the bottom. And you divide them, you find their quotient. You say, okay, if I have like a 3x squared plus 2x divided by a 2x squared, why not? That's it. Well, no, because that would factor out plus 4. There we go. Notice how the degree on the top and the degree on the bottom match, right? This is a 2, this is 2. Now, if the degrees on the top and the bottom match, what I do is basically say, okay, that means that the horizontal asymptote is going to be 3 over 2. I just take those guys right off, and that's my horizontal asymptote. So this would occur at y equals 1.5. The horizontal line would be at 1.5. Okay. So those are the rules. You just got to memorize those. That's right. You know what they're right. All right. Identify the zeros and the asymptotes of the function in the graph. Again, we're going to use our graphic calculator to help us out a little bit. But okay, so now notice how it does not say just the vertical asymptote. It says asymptotes, right? Plural. Okay. So first off, let's find the zeros. Now, again, that did not change. I find the zeros of the numerator. X squared minus, x squared minus 3x minus 4. That factors, and again, I'm finding when that equals 0. It's x minus 4 and x plus 1. So I've got x equals 4 and x equals negative 1. So that means, well, those are my zeros, right? 4 comma 0 and negative 1 comma 0. All right, now I can go here, 4 comma 0, negative 1 comma 0. Now, the vertical asymptote, same rule that we had before. The vertical asymptote is x equals whatever the denominator is, 0 in this case, like what makes the denominator undefined, x equals 0. So that means my vertical asymptote in this case is my, don't curve around. Ooh. Can I move me? There we go. Is right here. Okay, now my horizontal asymptotes. Okay, my horizontal asymptote, sorry, singular. My horizontal asymptote, if it exists, okay, is it top heavy or is it bottom heavy? Okay, the degree on the top is 2. The degree in the bottom is 1. It's top heavy. Degree in the numerator is greater than the degree of the denominator. Guess what? It has no horizontal asymptote. None. Or you could write DNE does not exist. Right, that's acceptable too. Okay, so at that point, let's go to my calculator, just like we did on the last couple problems of the last section. Look, they're still here. X squared minus 3x minus 4 over x, just an x. Delete. Got that. Put that right there. Just sketch that in. Okay. Looks like it comes up here and dives out around here. Ooh, kind of missed it. That's all right. Can I move it? Doesn't really matter. Doesn't really matter. There we go. All right, so there's my function there. All right. Okay, so zeros. Again, my task is zeros, vertical asymptote, horizontal asymptote. All right, now my zeros where the numerator equals 0. Okay, that's easy. X equals 2. So this only has 1 0. Interesting. Now the vertical asymptote, or should I say vertical asymptotes? It's when the denominator equals 0. Okay, x squared equals 1, square root it plus or minus 1. Ooh, and I should go back and I should say this is at 2 comma 0. You know, we should be a little bit more specific. Why? Because in our vertical asymptotes, they are x equals numbers, and those are vertical lines. So, okay. So we have a vertical asymptote. I'm going to change colors here. And I've got to be a little bit more particular with my dotted lines. I'm just going to get close in here. -1 and a +1. There are actually two vertical asymptotes because it's a plus or minus 1. All right, now, is there a horizontal asymptote? Okay, well, look at the degrees. The degree on the top is 1. The degree on the bottom is 2. Okay, it's bottom heavy. The degree on the bottom is bigger than the degree on the top. So what does that mean? That means that it's at y equals 0. Okay. Horizontal asymptote is y equals 0. Okay, so that means I'll make that purple. Now you may be thinking to yourself, well, wait a sec. But the idea of an asymptote is that it doesn't cross that, right? Not exactly. The idea of the asymptote is that it goes close to it. Okay, now watch here. So that's all we have right now. Let's go here. This is the original problem. X minus 2. X minus 2. I should have put that in parentheses. And over divided by, squared minus 1. Right. I like what's happening here. Ooh, interesting. So I've got, now again, this is just a sketch at this point. Let me bring this in here. Okay. So let me put it in blue. What's happening here? So the idea of the asymptote is actually occurring right there. Okay. It's getting closer and closer, but never reaching it over there. It looks like I've almost got this like quadratic-y looking type thing in here. Really skinny U shape. Sorry for the poor graphing. And then over here, now, it looks like it crosses that, right? It looks like it crosses that. So let's, when we want to investigate a little further, let's zoom in a little bit. I'm actually going to zoom. This is where zoom box is actually going to help me a lot because I want to know what's happening like right here. Let's open up this box right here. I want to know what's going on right there. It is going through. It is going through. So it's going through, and then watch what's going to happen. If I go to my table, see what's happening past what is my 0 there, 2. So at x equals 2. Okay, it hits 0. It goes up for just a moment, and then it starts to come back down. Okay, at 3, it's at 0.125. At 4, it's at 0.133. At 5, it's 0.125. So it goes up and then comes back down. Okay. So here, and I'm going to over-exaggerate. And then down. All right. Uh-oh, my kid's calling me again. Hold on, I'm pausing. Oh, we're going to move you. Okay, we're back. Sorry. All right. So again, it went right over there. I'm pointing like you can see me. It went up, over, and down, right? So it did actually cross through, but it went up and then back down, okay? All right, let's do one more of those. Okay. So first thing we want to look at where the zeros are. Okay, the zeros are where the numerator equals 0. So in this case, add the 12 over, divide by 4. X is 3. So 3 comma 0 is the only 0 here. Now, the vertical asymptote, where the function is undefined, at x equals +1. X minus 1 equals 0, so x equals +1. All right, so that means a vertical asymptote. Actually, you know what? I'm going to switch colors here. What? What are you doing? Get out of here. That was weird. Okay, and then we do for the horizontal asymptote. Now, we look at the degrees here, and what do we notice about this? The degree is 1 here, the degree is 1 here. So that's y equals, if they're even, this is the rule. Leading coefficient of the top divided by the leading coefficient of the bottom. Okay, so that means 4 over 1. Oh, okay. So that means it's y equals 4. So horizontal asymptote at y equals 4. Ooh, kind of went above 4 a little bit. Sorry. All right, so now when I go to graph it, let's put it in red here. I go to my calculator again. It's 4x minus 12. Where's my calculator? Parenthesis 4x minus 12. My young one is, not my young one, my 3-year-old is playing in a rice bin down there. All right, tablet time ran out, so we got the sensory bin going. But she seems to be getting a lot of rice outside the bin. All right, 4x minus 12, and we've got divided by x minus 1. Let's see, x minus 1. Okay, photograph that. Oop, of course. I zoomed in. Oh, good. See that part of it. Zoom 6 back to normal. And it looks like it's up here. And down here, it looks like it crosses through and then hits almost down there. In generalities, right? We could plug in points to see where it's actually hitting, but it's all right. We don't need to do that. Sadie, you keeping it all in the bin? Yeah. Keep it in the bin, okay? All right. Last topic we'll discuss here is holes in graph. In some cases, both the numerator and the denominator of a rational function will equal 0 for a particular value of x. Basically, this happens when there's something on the top and the bottom, a factor on the top and the bottom that cancel each other out, and it goes away. Okay, so it looks like it's not there, but there, what arises is now a hole in the graph. Okay, a hole in the graph. Okay. All right. So here's the general rule. If a rational function has the same x minus b factor in both the numerator and denominator, there is a hole in the graph at the point where the original function had x equals b. Okay, that point, like that, if it was like x minus 2 that canceled out. At 2, we'd have to run that value to see where the hole would end up. The hole would be at x equals 2, almost like a vertical asymptote, but it doesn't lie, like it doesn't like come up close to it like an asymptote would. It was just like the line would come together and then there would just be a hole sitting there. Okay. So what do I mean by that? Take a look at this one. There was not another thing in there. No. Okay, that's right. All right, identify the holes in the graph of each function, then graph. All right. So we've got x squared minus 9 and x minus 3. So if I go to factor things down here, that means I've got an x minus 3, x plus 3 in the numerator, and in the denominator, it's an x minus 3. Okay, notice how the x minus 3's cancel, right? So this function factors or reduces down to x plus 3. So f of x really reduces down into just x plus 3. What does that mean? That means this function looks like this equation, which just is linear, right? Y-intercept of positive 3 and slope of 1, right? Okay, let me make a line as good as best I can. Yikes. Yeah, that's all right. All right, now, however, there was a point that is undefined here, right? Take a look at what canceled out. The x minus 3's canceled out. So therefore, I have to look here. X minus 3 equals 0. That can't happen, right? because of the denominator. X can't be 3. So therefore, there's a hole in the graph. This function cannot be equal to 3. Right? The x value of 3 is undefined. This function is continuous at 3. 3 comma what? Well, run it through. 3 comma 6. How did I know that? Well, f of 3 would be 3 plus 3 or 6. So that means at 3 comma 6, let's see how well I graphed. 3 comma 6. Hey, not bad. I have to put a little hole in the graph. 3 comma 6 right there. And I represent it. Ooh. That hole should be a little bit more centered on that line, but that's okay. That basically means that at 3 comma 6, this function is not defined. This f of x graphs like, acts like, she's getting rights everywhere, acts like x plus 3, right? But with one exception, the hole in the graph at 3 comma 6. Let's do one more. All right, so I take this one here, x squared minus 3x plus 2. Right? If I factor down the numerator, it's x minus 2 and x minus 1, right? Factors of 2 that add to get to negative 3 are negative 2, negative 1. And then in the denominator, factors down x over x minus 1, which makes sense why I'm doing this here. That cancels. So this function acts like f of x is equal to x minus 2 over x. Okay, now what does that imply? Right, what does that imply? Well, I now have to graph this. Well, we know how to graph it. We just finished graphing those things, right? So that means that there's a 0 at, the 0 is at x equals 2. There is a vertical asymptote at x equals 0. I should change colors here. There is a horizontal asymptote. Ooh, the degrees are equal. So the horizontal asymptote actually happens at the leading coefficient at the top, which is a 1, divided by the leading coefficient at the bottom, which is a 1. So y equals 1. So that means there's a horizontal asymptote at 1. Okay, now let's graph that. Let's see what that function looks like. This x minus 2 over x. Okay. This x minus 2 over x. Parentheses x minus 2 divided by x. I'm going to go to graph that. Okay, makes sense. This function here looks like it's right here and right. Ooh, don't cross the asymptote. Undo. Right there. Okay. Now, with one exception, right? That's what this function looks like. But we know that at 1, this function is undefined. Okay, where 1? F of 1 is, well, if I plug that in here, 1 minus 2 over 1, negative 1 over 1, negative 1. This hole is at 1 comma negative 1. So I have to go back in and erase away 1 comma, ooh, I kind of graphed that poorly. I'll fix it right now. 1 comma negative 1. Put a little open circle at 1 comma negative 1. There we go. Make that connect down there. Sure, there we go. So visually represent the whole. Visually represent the whole. Okay. So I hope we're having a good day. Sadie, do you want to say bye? Bye. Sadie, say bye. 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 Okay. Hope we're having a good weekend. Happy Easter, everybody.